Well, happy to be here today to tell you about ScalarLM. I'm Greg Diamos. I'm one of the authors of ScalarLM. And let me tell you a little bit about my background before I dive into this. Before ScalarLM, long ago, I was an architect on CUDA at NVIDIA. I worked on the software stack that was used to program GPUs. This was before deep learning. And I think the most useful thing I ever did for CUDA when I was working on CUDA was I did the first large-scale deployment of deep learning on CUDA, which was at Google Brain and then eventually Baidu. And we built a 4,000 GPU training cluster. And we discovered all sorts of things along the way. Many of those learnings are kind of going into ScalarLM, which we think of as a maybe modern platform that allows you to train LLMs and run inference on LLMs. So you can build more things than just building LLMs. And a couple of the other lessons that kind of are getting folded into this, one was emphasis on performance and benchmarking. This is kind of the bitter lesson of if you can just train one of these models on more GPUs or with higher performance, then we can often translate that into greater capability. So we released MLPerf and MLCommons, which are benchmarks that measure the performance of deep learning systems. So I'll talk a little bit about benchmarking, and especially benchmarking on new accelerators. So I'll talk about benchmarking on AMD GPUs in addition to NVIDIA GPUs. And so that's a little bit about me and kind of, a little bit of the motivation of this. Here's an outline of the talk. So first, we're going to go over some trends in new AI workloads. So of course, the field is moving incredibly rapidly, as I'm sure everyone here has seen that in the other talks. And we're starting to see models that reason. And I'm also going to include some information that I've learned of talking to AI researchers of just some thoughts on where the field currently is and where it could be going, over the next few years. And then how is that going to change the infrastructure that we run on? So ScalarLM, you can think of it as sitting at the layer that performs training and inference for LLMs. Typically, these are separate stacks, and so the key difference in ScalarLM is that it's unifying them together into a single framework. And then we're going to look in some aspects of benchmarking on AMD GPUs. Of course, benchmarking on NVIDIA GPUs has been extensively covered, and so I'm not going to go into too many details of that today, but I'm going to add a few comparison points, and we're going to start building our way up to complete application benchmarks on AMD GPUs. So we'll take a few steps towards that today. So that's kind of the talk, and let's just dive into it. Okay, so this is speculating about the future, about where we currently are and where we're going. So I think for me, one of the things that we found in Baidu actually in 2017 was that these models scale predictably. So these are now called LLM scaling laws. And LLM scaling laws, from my perspective, this is a slide from Ilya's keynote in NeurIPS. I agree with Ilya that they are the driver of all the progress that we see today. That they kind of take us on a natural progression from GPT to GPT-2 to GPT-3 to ChatGPT to GPT-4 to the reasoning models that we have today, and that they keep going. And that they keep going is actually the most interesting part, because as they keep getting smarter and they keep learning and we keep reducing our error rates, the capabilities that they have keep increasing. New abilities emerge from the LLM so that they can solve harder problems, and we can use them, in places that we hadn't thought of before. So LLMs are going to keep getting smarter. That's the takeaway from this. You want to think that LLMs are not, as smart as they're ever going to be. They're going to keep getting smarter. And I think one of the things that's been difficult, though, is, of course, scale. These things require running on enormous systems. They require running on hundreds of thousands of GPUs for months in order to get to the GPT-4, GPT 4.5 level that we have today. And that's really expensive. So it makes a lot of researchers start scratching their head and think, like, maybe there's a better way. Maybe there's a way that we can train these models even more efficiently and even faster. And so this is also a slide from Ilya's keynote where he says, oh, look at this example of nature. Look at humans. If you look at the size of the animal versus the size of the brain, they typically follow these black lines of a a scaling relationship, but it's also possible to break out of the scaling relationship. So humans break out of the scaling relationship. And so I think this is a topic that's on the minds of many AI researchers of how can we scale faster and more efficiently than scaling laws. It's amazing that scaling laws even exist at all, but what are the reasons why we have to be bound to scaling laws? And so what would that enable? I personally am, in Ilya's camp with this. I think it's possible. And so I'm going to talk next about what that would enable. So this is a web app. This is an application that was written by Claude 3.7. It's about a 2,000 line React app that was completely written from taking a different map data and then writing the React source code. And then, you're kind of seeing how you can interact with it and see the web app. This is something you have to pay a developer for. Or it might take a developer like a week or many hours to build even a few years ago. But today an LLM can generate it in 10 seconds. So if you extrapolate forward with scaling laws, the expectation is that simple problems like the problems that we have today, like writing 2,000 line React apps, of course, will be possible, but LLMs will be able to solve even harder problems. So these are some hard problems that we've seen from talking to various industries of what they wish they could apply LLMs to, but where LLMs are not quite there today. So LLMs today can't write the Tesla autopilot software stack from scratch. It's a little bit beyond them. They can't write operating system drivers from scratch. They can't write major pieces of drug discovery pipelines, and they can't write complete data transformation, relational data views or systems or data stacks that large-scale enterprises have. So they can build pieces of these, but they can't build them completely. But the expectation is that with scaling laws, these new applications should become possible over the next 10 years, and maybe even sooner if new algorithms emerge. So what would the new algorithms look like? So the next part of the talk, I'm going to talk about a framework that I'm calling super alignment to think about this new class of algorithms that scale faster. And I'm going to give one concrete example. So we're going to look at what kind of software stack you need to run these things. What do they look like, and what kind of software do you need to run them? So I think DeepSeek is a first step towards super alignment. So we're saying, chat was great, goodbye chat. Reasoning is better. Thinking through, how to respond is better than just responding directly. So what does that mean? So we end up with these kind of, this is maybe like a high level view of what this looks like. So you can start with basic LLMs, the pre-trained foundational models like Llama 3, Llama 4. You can add additional data resources to it. Super alignment is going to, but you can also steer it. So you can also, if you wanted to solve a particular problem, like you want it to be better at writing apps, or you want it to be better at writing relational software, data transformation software, you can tell it that, and you can provide it resources. And then the super alignment algorithm can kind of use the foundational pieces of the LLM together with the new data, together with the aligned goal that you have, to produce a new LLM that's smarter and better at the task. So let's make it more concrete by looking at R1 as an example. So how does this work for DeepSeek R1? So you have the base LLM. It has additional data resources. It can, it's learned skills like to speak in English or to write code. And it potentially has access to tools through adapters. That model, when you put it into this reinforcement learning setting where you have a reward function. So the reward function is going to decide whether or not the task has been solved, whether or not the model is performing well. The LLM can think step by step in English, so you can read it. It can think step by step about how it will solve the problem. And so it generates these reasoning trajectories. It might try solving the problem in multiple different ways. Some of them are effective, some of them are not effective. The reward function decides which one is effective. If it solves the problem, it's effective. Those generate a reward signal, which is used to train the LLM. So the LLM, using its foundational knowledge, trying out new problems, can learn to reason, and it can learn additional skills beyond reasoning. But I think reasoning is a great one to start with because it's very concrete. Okay, so now hopefully this gives you a glimpse of what the future applications look like, that the LLMs are getting smarter. We're developing more advanced methods for training the LLMs, like reinforcement learning with reasoning in DeepSeek. And what does it look like when we start running those on real systems? So now we're going to look at ScalarLM, which is an open source framework that we built that makes it easier to build applications like DeepSeek R1 and superalignment. So the reason why we build ScalarLM is because we kept trying to build applications like this. We kept trying to build reasoning loops like DeepSeek R1, and the infrastructure kept getting in our way. We realized that we needed both training and inference. And so typically these things are separate frameworks. Megatron is a really great framework for training, but VLM is a really great framework for inference. Hugging Face has a very large library of models, but it was very difficult to put all these different pieces of software together to write even a simple application like the one that I just showed you. So that's why we built ScalarLM, to make it easier to build applications like this. We made a fair amount of progress on ScalarLM, although it's in beta. It's a v0.5. We're working towards a 1.0, maybe in the middle of the summer. But we're able to train 100 billion parameter LLMs. We can run training and inference on these TensorWave nodes. TensorWave is a AMD GPU cloud that provides access to MI300 today. So these machines have quite a lot of memory capacity, so you can put on pretty big models. You can see that this is using, maybe 30%, 36% of 4 GPUs to run about a 100 billion parameter model. So they can fit quite large models. And these are some of the scales of models that we're able to train today. One of the interesting things about ScalarLM and this whole ecosystem is that there's a heavy emphasis on open source. So ScalarLM is CC0, the most permissive open source that you could possibly think of. There is, the entire thing is developed in the open. And we would just want to make sure that this is available to the community and that the community has this capability. But it kind of fits in together with some of these other great open source libraries like VLM, Hugging Face, PyTorch, the Llama ecosystem, including the software stacks and the models. So it's actually possible to do quite a lot with open source today. This is just a figure that shows where ScalarLM fits in with some of these other frameworks. The biggest thing here is that it includes training and inference. So most of these frameworks focus on training or inference, but they cannot do training and inference together. Or you require the user to stitch them together to get a stack that can do both. So that's the main difference that we're trying to add. And then another important thing is that ScalarLM has mainline ROCm support. You don't have to work on a separate development branch. It's covered by our benchmarking and regression testing, which I'm going to cover a little bit later. So this should work really well on AMD GPUs in addition to NVIDIA GPUs. Okay, and then I like Llama Stack because I think it has a pretty good perspective on the different layers and kind of how they fit together when you're building applications on top of LLMs. So the Llama Stack kind of has this concept of providers, which provide access to these higher level blocks at the top. Like if you want to build agents or you want to do post-training, you may need things like memory, or you may need to do inference, or you may need to be able to do evals. And then all of these things are kind of built on top of service providers. And so just to understand where ScalarLM fits in the ecosystem, it's at that service provider layer. In Llama Stack, as you can kind of see here, they have a vision for training and inference from service providers, from maybe even a single service provider. But the ScalarLM today is probably the first real implementation of that, where it actually implements both training and inference. Okay, and then this is our high-level architecture, and this is how we get up to training and inference. The interfaces end up being pretty similar, and they're fairly standardized now. So the industry is standardizing inference around completions. We have one extension to completions where we can run completions on a batch, so you can submit 10,000 requests in a single request to this system. But you can also plug in an OpenAI client, and we get that because we build on top of VLLM. And then the difference here is we also have the concept of train, where train takes some data and a model and then produces another model. And then the models, because they're unified, because training and inference is unified by this model connector at the bottom, you can start calling completions or generate on the trained models. immediately without having to go through separate deployment steps. And that's kind of what we mean by unifying training and inference, having a single stack that provides both of these APIs. Okay, so that's a high level. I'm going to also just add some highlights of why this is difficult and how we put these different layers of software together to allow this to work. So if we want to train big models, of course, it's computationally intensive. They don't even fit on one GPU. So we have to think about distribution strategies. How do we spread them out over multiple GPUs? This is what frameworks like Megatron do. But we also have to tap into this huge ecosystem of models. So how does that work for one model versus another model if they have different layers? Like how does that even work? So this kind of shows the approach. This is code from ScalarLM that shows how we do this. We tap into Hugging Face. So we use auto model for causal LM, which is the Hugging Face transformer's way of instantiating a model out of their vast library of thousands or tens of thousands of models. We do visitor patterns. So we actually run passes over the model graph to, for example, add adapters. In this case, we're adding token former adapters, which we think of as a very efficient way of adding additional parameters to the model. And we can also apply distribution strategies. So we can go through and apply FSDP, tensor parallelism, data parallelism to these models that have been loaded out of Hugging Face by inspecting the layers and inspecting the tensors and figuring out how to shard them and distribute them. And so at the high level, this is actually putting together, even though it's simple here, it's putting together an enormous amount of software in order to make all of this work. Okay, so I want to show an example of what you can do with this. I'm going to show a text to SQL example. This is a common example for LLMs. They're going to write code that's used to process data. So SQL is, of course, the language, most commonly used language for communicating with databases and querying databases. So BERT is a example set of databases and queries, SQL queries. So this is what implementing DeepSeek R1 style reasoning so that the LLM learns to generate better SQL queries. This is what it looks like in ScalarLM. So we can do the entire loop in 19 lines of code, and we don't have to do any deployments. So we can import a ScalarLM client. It's connecting to the server, maybe the TensorWave node that I showed you there. We can run inference to eval the LLM. We can run inference to try out different reasoning strategies, to try out different reasoning trajectories. We can run inference to judge the trajectories to see which ones are working and which ones are not working. And then we can train the LLM on the trajectories that are working or with the knowledge of the trajectories that aren't working. So we can call train on line 17, and then that model, as soon as it's finished training, can be immediately used for inference on line 19. So you can write these really compact loops that include training and inference and build much higher level applications like reasoning if you have the ability to do training and inference. And it's pretty effective. So this is, again, think of this as a hello world, hello reasoning example, but it boosts accuracy pretty significantly. If you take Llama 3 or Llama 4, you can get a 20 absolute % increase in accuracy by this loop, 19 lines of code that I just showed you. So connect your data, give it a try, have the model try it, learn from what's happening, and it can become a better model very quickly and easily. Okay, so the code is available if you want to try this out. I would love to be able to copy and paste into the chat, and I'm just going to do that. Here we go. Okay, so we made it through the first 2 sections. I think I've got about 5 more minutes here. So I'm gonna, in the last 5 minutes before I take questions, by the way, if you have any questions along this, please add them to the, click the toolbar and then click the QA button and then, write in your questions. I'm happy to answer some questions. The last section I'm gonna look at is benchmarking ScalarLM and starting to provide some performance data of running this kind of functionality, LLM training and inference through a unified stack on AMD MI300. So AMD, has been building GPUs for AI for a while now. They built this ROCm stack, and they've released, MI300. You think of it as maybe the 3rd generation of accelerators or GPUs that are optimized for AI. And one of the things that we found, I think we're one of the first stacks to build on top of AMD. And so we kind of have to build a lot of things up from scratch. And one of those things is a clear understanding of performance. In order to get performance at the high level, like maybe at the MLPerf level, which is, think of as entire training workload, large-scale training workloads, or large-scale inference workloads. At the MLPerf level, we have to start from the building blocks. So we have to make sure that the fundamental operations that are being performed when we're doing training or inference are performing well. And so there's already been a lot written about that in the NVIDIA ecosystem, but there's been comparatively less because it's newer in the AMD ecosystem. So that's what we're going to start by introducing here. So I'm going to first take a look at these two GPUs. So there's AMD Instinct MI300. There's also H200. These are GPUs that came out around the same time. And they have similar specs on paper. AMD has a little bit more memory. It has about 200 gigabytes of HBM3. H200 is around 150. The memory bandwidths are pretty similar. They're both around 5 terabytes per second. AMD is a little bit higher, NVIDIA is a little bit lower. But this just kind of gives you an idea of the specs and some GPUs that you might think about running these workloads on today. So these are the published specs. So the next thing we want to do is kind of build up from that into measuring them. So this is maybe a first benchmark that we're going to look at, which is just a memory bandwidth benchmark. So this is called memcopy, like copying memory. How good is the GPU at moving memory around? This ends up being relevant for the workloads that we're looking at because when we're moving the model's weights around, like imagine you're loading the weights of the LLM or you're loading the activations from the KV cache in the LLM, then you end up copying memory. You end up moving memory from HBM into the GPU. And so this benchmark measures how fast you can do that on the MI300 benchmark or on the MI300 GPU. So the x-axis here is kind of looking at different data sizes. And then the y-axis here is looking at the bandwidth, gigabytes per second. So how close to that 5.3 terabytes per second can you actually get in practice? And I also want to note that this is using our entire software stack. So this is using the real images, the these mem copies are going to be moved around when we're allocating tensors and moving tensors around. So they're at the very highest level of the software stack. They're not down in the, I'm programming a DMA engine and I'm trying to measure memory bandwidth. So this is kind of indicative of what you can see if you write a kernel or you write a model and you try and move the model around. So you can see, compared to the roofline, best possible performance according to spec, 5.3 terabytes per second. You can kind of get up to about 50% or 60% of that, but you have to have transfers that are over about 10 megabytes. And then as you increase the transfer size, the largest transfer sizes here around a few gigabytes are the sizes of the embedding tables in models like Llama 3 or Llama 4. So they're like the last layers, the biggest layers in those LLMs. The takeaways here, I think, are that it's actually possible to get pretty high utilization. Like I think a gold standard for memory bandwidth is maybe 80%, but getting 50 to 60% is still quite good. There's only maybe 2x or 1.5x you could squeeze out of this, according to the theoretical max. So this is still pretty good. So perf, for basic operations like memcopy on MI300, actually pretty good. This is a good foundation to start building like a more complete application on top of this. So if you want to dig more into this and reproduce this, we really believe in getting the context right and reproducibility. The source code for the benchmark is available, and we also have a blog that has like a much more extensive analysis of this. And this is just the beginning. So I don't have time really to cover everything today. I'm going to start. I have to start somewhere. So we covered memcopy. This is our benchmarking roadmap. We're kind of going through memcopy on a single GPU, memcopy between GPUs over the infinity or the NVLinks. We're looking at the math-heavy kernels like matrix multiplication and attention for sizes that are found in real LLMs. Then putting all of those pieces together into benchmarking inference, benchmarking training on single nodes, distributed training across different GPUs in the same node, benchmarking the links. One of the questions is, NVLink versus InfiniBand versus Rocky. How do these things stack up to each other? We use MPI as the communication library. So we have benchmarks that cover those. From there, we go to multiple nodes, and from there, we go to multiple nodes with reasoning. I'm kind of using inference and training, like that application that I showed you. So stay tuned. We're going to trickle these out maybe, once every few weeks. Okay, but stay tuned. So that's a sneak peek of benchmarking and where we're at. Okay, so that's really it. I mean, I think I covered all the material. You got a glimpse of, some of the workloads people are building and how they might map to, an LLM software stack, how ScalarLM kind of puts together multiple pieces of these open source software. It itself is open source and allows you to run reasoning loops like in R1. And then we saw a sneak peek into memcopy performance on MI300, which seems to match the specs. If you look more broadly in the community, I think there's a few benchmarks, mostly from semi-analysis that have covered MI300 performance. I think it'll be interesting to compare both of these things as they come out. Okay, so if you're interested in ScalarLM, try it out. Again, it's open source, it has a CC0 license. You can learn more about it at scalarlm.com. Give us feedback. We're in an active development and feedback phase. So we'd love to have contributions and feedback. Okay, that's it. I'll be happy to take questions. All right, one question is, how did you find ROCm support on MI300X for writing performant kernels like flash attention for both training and inference? Is there any libraries like AITR, or do you write your own kernels, or is it still work in progress? I think a good way to understand kernels, like kernel development on AMD, is to go through and build the kernels that are already there, that have been already developed, that are kind of aggregated together into ScalarLM. So let me paste something on here. Just give me a second. So we have this repo that's called ROCm base, which kind of goes through. I'm just going to paste this into the chat. This goes through and builds about 15,000 kernels, and they're drawn together from multiple sources. So I think just running this and building this Docker file and just watching what gets built and which libraries are used and how the kernels are implemented will give you a good idea of what the AMD kernel development ecosystem looks like. It'll like sample all of them, and it'll tell you, where different important kernels are coming from. So I think that could be a good way to kind of orient yourself and see what development on AMD looks like today. Okay, I'm going to switch back to questions, and let's see. I think let's see. I think some people were raising their hand, but I actually don't know how to call on you if you're raising your hand. So yeah, I think I'm also feeling like I'm probably at the time. But here, there's a new question in there. Okay, so another question is, agree on the importance of unification of training and inference with the resurgence of RL. How do you compare ScalarLM with existing stacks, VERL, OpenRLHF? Let's see. I mean, I think our philosophy is to try to include kind of the best of all of these things. I think we're not really trying to take an opinion about like a particular RL algorithm. We're really trying to, like RLHF, as an example, we're trying to provide the building blocks. So in the figure that I showed that had these, OpenAI client completions API and then train API, we're really just trying to figure out what are the building blocks of so many of these RL algorithms, so that people can experiment and try out different approaches. We're also pretty opinionated about the importance of scale. So it's kind of in the name of ScalarLM that a lot of these frameworks, you can kind of focus on the implementation of the algorithm, or you can focus on the scale. We're really more focused on scale because we think that, through scaling laws, these methods, even if they work out on a small scale, and we can prove them out on a small scale, to get the most value out of them, you're really going to have to run them on, hundreds, thousands, tens of thousands of GPUs. So yeah, I think also our philosophy is that we're going to try to take the best of open source. Like you might have seen that, we're already incorporating Megatron, and we're already incorporating VLLM. So if there are, great implementations of RL algorithms, we would love to figure out, kind of how to work together with some of these frameworks so that we can provide interfaces that they can tap into so that they can get to scale. So I'm not sure if that completely answers the question, but I also say it's an emerging area, and so the software stacks are also emerging. So usually when this happens, if you fast forward 6 months from now, we'll probably have good frameworks that will, be really easy to use, and it will be high performance. But today, we're really just starting to see the first libraries, and I think more development is good. Okay. Let's see. Thanks for the talk. Are there any low budget ways of accessing MI300X for startup? So yeah, it is a real thing that when there's a new accelerator that comes out, it's harder from an infrastructure perspective to get access to it because it's not going to be available in AWS or Google, and you can't just click a button to allocate an MI300 node. I think the GPU clouds like TensorWave are making it easier, so it's way easier to run something on like a TensorWave node than it is to buy your own GPUs and build your own data center. But I'll just note like that's what I did 3 years ago. That's what we did in the early days of CUDA too. In 2012, there were no CUDA clouds, and the public clouds wouldn't accept them either. So I think you can try out things on a small scale. I do know that you can go look at the ROCm device compatibility list, and some of the consumer GPUs that you could buy and put into a desktop are supported by ROCm, although that wasn't true even a couple of years ago. So yeah, I would say first, if you're really on a shoestring budget, try out one of the consumer GPUs. If you're like more of a startup and you're thinking like, okay, I'm more interested in a node, you might want to try one of the GPU clouds. But I expect it to get better over time, but also the people who are willing to invest early and try it, even though it's difficult, I think will be able to go faster. Great questions. Okay, I appreciate all the questions. I think we're way beyond the time that I was supposed to stay here, but I haven't gotten kicked out yet, so happy to stay on a little bit. Let's see. Regarding MI300X, you could use one of the GPU providers like VAST or RunPod for larger workloads. Might be worth speaking to AMD folks. I think that's a fair point. I think if you're AMD does have a startup program, and I think that's I think it's great for people in the comments. The whole ecosystem is moving so quickly. I actually don't even know all of the different places that AMD GPUs are available because they're just starting to spring up everywhere. I didn't even know they were available on RunPod, but that's great. I think if you can't find it, if you look around and you can't find it, I would say one that I've had pretty good experience with is TensorWave, and I also have had pretty good experience with AMD. So if you're a startup and you're working on something interesting, like AMD isn't spending all of their time servicing requests from OpenAI. So they realistically do have more engineering bandwidth that they can engage more deeply with builders today. So you could definitely contact them too. Okay. Great. Appreciate all the questions. Okay, I'm at the top of the hour, and now I'm hitting my time constraint. So yeah, appreciate everyone attending, and yeah, good luck building.